And take our seats. There's some nice munchies that Ann has provided, and a lot of Halloween candy, which I'm hoping you guys will take all of it. Because I got here first. We can trickle it out over time. Welcome to for our presentation today. Of course, this is Ann Abuelos' master's thesis defense. The best defense is a strong offense. And I'm going to be really nice to her because she's got it done on her shirt. Ann earned a bachelor's degree in fisheries, wildlife and fisheries, wildlife fisheries at Louisiana State University in 2008, six. And she just told me this. And then worked as a technician at the University of New Orleans for 3.5 years, and started at FIU in 2010. And so she has completed her master's project in a timely fashion. And today she's going to tell us about her findings. She's made a couple of presentations at national meetings, posters, and an oral presentation at the American Fisheries Society this summer. So, Ann.
All right, thanks, Joel. I am attempting to record this online. It's a little distracting because I can see myself in the computer and it's like staticky, so hopefully it's working. In fact, I'm going to minimize this because otherwise I'm going to stare at myself the whole time. Alright. So thank you all for coming. I hope you have some coffee and food and help yourself if you like. So the title of my thesis is Spatial and Temporal Patterns in the Distribution, Behavior, and Activity of Fishes and Canals of the Everglades. So this is just an outline of my talk. I'm pretty much going to go through my thesis in the order you would expect. I'm going to kind of pair my stats and results together, and I have it organized by the 3 questions that I sought out to answer. So to jump right in, predators can impact prey via 2 pathways. The first is more obvious, in that they capture and kill the prey, causing a reduction in prey density and a possible increase in predator density. And this can lead to indirect effects on the prey's resource, such that a decrease in the prey can cause an increase in their resource, which is typical of a trophic cascade. Now, just the mere presence of a predator can impact prey. So here we have a whole bunch of swimming fish that are responding to this very larger predator in the background. And these can also lead to indirect effects on the prey's resource. So a predatory ant causes a caterpillar to move off of the cotton plant instead of foraging on it, which then has a positive effect on the cotton plant. Now, the emergence of these effects depends on a whole slew of variables. So if there's any sort of behavior that the prey has to deter a predator, so to say the ornate horned lizard shoots blood out of his eyes to deter a predator, as well as the predator's hunting mode, is it a sit and wait versus cruising predator, and features of the landscape, the amount of connectivity or edge habitat can influence the way predators and prey use the landscape. Now, just like everything in nature, there's going to be some sort of temporal variation. So I like this picture. It's just, I got a flicker plankton that was collected at night, which is the left-hand jar, versus plankton collected during the day. So the way they use the water column varies on a diagonal basis, as well as predators. And Mike, I took this from your website, so thank you. It was just a very clear-cut picture of how this tiger shark predators vary on a seasonal basis. So in the winter, when you go to the blue bars, you see a significant decline versus the summer. Now, disturbances that affect the landscape also impact the amount of spatial overlap between predators and prey. So here in the Everglades, seasonal drying of the wetlands causes smaller fish to congregate in these alligator holes. And then you have all the wading birds that come in and forage and have a delicious meal. Similarly, in the African savanna, we see both predators and prey using a very scarce resource. Now, predicting the effects of predators on prey requires knowledge of their density. So when and where are they in the landscape, as well as what happens when they come in contact with one another, what sort of behaviors do we see. And then using encounter rate, which is just the rate at which a predator encounters a prey over a period of time, can help us understand the effects of predators on prey. dangling in the water. Okay, so in the Everglades, our prey here are smaller fishes. And they're mainly influenced by features of the landscape, such as the amount of connectivity, this risen flue habitat that is characteristic of the Everglades, as well as localized features, the amount of submerged aquatic vegetation, how high the water is. So these are our main drivers in smaller fish. And smaller fish are a very important food source for wading birds. What we don't know, or what we don't have a very good idea of, is the effect of larger piscivores on smaller fish. And one place where they may be particularly important are in canals. So approximately 300 kilometers of canals have been dragged throughout the Everglades over the last century and a half. And these deep water trenches are used quite a bit by larger piscivores. And so during the dry season, when water levels recede in the Everglades, we know that small fish start to move towards these habitats if they're near them and use them. And so it leads us to wonder, well, what happens when we put both these larger fish and smaller fish in the same habitat for a period of time? So some of the larger piscivores I'm talking about are the Florida gar, as well as a whole slew of sunfishes, the largemouth bass, and bowfin. And we know from gut content data that these guys feed on smaller guys, like the juvenile sunfishes, the eastern mosquito fish, amongst others. So the goal of my study was to examine diel and seasonal patterns in fish using canal habitats, and then using counter rates to assess the level of predation risk for smaller fishes. And I sought to answer the following questions. So how do seasonal and regional declines in marsh water levels influence fish use of canal habitats? And then how do changes in hydrology affect the behavioral response of smaller fish to large fish? And lastly, is there a diel pattern in the risk of predation for smaller fish? So I did this using a Ditson, and a lot of you have seen me give talks on the Ditson, so I won't go into too much detail. This is just a picture of it. I had it attached to this metal pole that's hanging off the side of the boat, and then that cord connected to a computer on board, so I can look in real time at what the Ditson is seeing, so I can make adjustments as necessary. And just in brief, imagine you're looking, over the canal. We're in the boat, and we're aiming the Ditson, which is a little white box, towards the marsh canal edge in the upper portion of the water column. And it's a multi-beam sonar, so it sends out 96 beams, and there's 500 pulse pixels per beam. So you get a nice high-resolution image. So it looks like that. So your view is top down. This kind of bright blobness is the opposite marsh edge, so some vegetation. The scale goes from around 2 to 6.5 meters. This is a little fish, and I'll show you a video in a couple slides. Now the pros of the Ditson is that I don't need light, so it was great for this study because I wanted to examine the diel patterns in fish now. I can sample multiple sizes of fish, and what I mean by that is I can sample both our smaller prey and our larger predators with one piece of equipment. And I can observe and quantify their behavior without getting in the water or disturbing them in any way. And it also avoids problems associated with some capture techniques like electrofishing, which tends to bias certain sizes as well as species. However, like any great piece of technology, it has its own set of cons, in that there's not enough detail to really get at species. So in my study, I grouped them based on their size. And the image is 2 dimension so that I could not distinguish the depth of where the fish was. So in that view, that top-down view, you see this dimension and this dimension, but you don't know where in the vertical column they are. And there is a trade-off between the field of view and the size of fish. So like I said, there was 512 pixels per beam. You can extend the Ditson 5 meters, 10 meters, 30 meters in length, your window length. And so the further you extend it, you're going to be stretching that pixel size. Your pixels are going to get larger, which means you can't detect as big a fish, or a smaller fish. So there's a trade-off there. All right, so to examine the seasonal component of my study, I worked in 2 canals, the L67C and the L31W, located down here. I sampled monthly from December to the following October, and then I grouped them into seasons, which I'll get to in the next couple slides when I pull up the results. I ended up dropping the December date for my analyses just so I have a balanced design. And then I had 3 sites in each of my canal, and I put 3 of these 5-minute videos per site. I averaged the metrics within each of those kind of sub-samples. So in essence, I had a sample size of 3. For the Daniel study, I added on another canal in C111. I sampled the following dry season in February, April, and May. I doubled the amount of sites I had, and instead of taking 3 of these 5-minute videos, I just took one long 15-minute video at one site. So I sampled 6, and I sampled during the day and at night. I used the EDA network to get water level data in the adjacent marsh to my canal, so I could predict when fish would be in the canal. And it's provided on 400 meter by 400 meter grid, which is important, and I'll discuss that towards the end of the talk. All right, so this is a video. You guys have seen this before. So again, your view is top down. This is sped up quite a bit, so the distance rocking a little bit, which is why you kind of see the outer edge moving, the fish moving in. So in each of these 5-minute videos, I counted the number of fish, and then I measured them. So this is just a zoomed in image of a fish. And then I standardized the number of fish to the per meter squared area. And I categorized my fish based on their size. So smaller prey, less than 12, and larger predators greater than 20. Typically in the Everglades, we call fish less than 8 as our smaller prey, but given the error associated with measuring in the software, I bumped up to 12 to ensure I was really capturing the whole prey base. And I wanted to focus on our larger predators, adult hydrivores, which is why I selected 20 centimeters as my cutoff. There was also the occurrence of schooling fish, and I defined a school in my study as a cluster of fish that showed uniform movement. So either they were moving together in unison, or I saw them changing direction. And then I wanted to characterize their shape so I could get at how closely compacted they were. So the closer the individuals within a school are to one another, that provides evidence that they're schooling as an anti-predator tactic. We do know fish school for a variety of reasons. So I am using the word schooling a little bit loosely here. So I used nearest neighbor distance and distance sensori to get at how compact the school was. And I used ImageJ software, which is a free software that you can download online. It's just an image processing software. I would export just a still shot of the school within a distance video. And then using some processing techniques in ImageJ, I would make it binary and kind of subtract out all the noise from the background. And then Essence would just count up all the little white dots, or the software would count for me, all the little white dots. And then measure nearest neighbor distance, is just the distance from each little white dot to its next nearest neighbor, averaged across all fishes in the school. And distance within Troy, the distance from each individual fish to the center average across the school. You get one number for each school. Now for the Daniel videos, instead of counting all the fish within 15 minutes, I divided up into 30-second clips and then randomly selected 10 to process. And I used Echo View and some methods developed by Kevin Boswell and others to get at the number of fish, their length, and their 2D swimming speeds. Because remember, this is a two-dimensional image. And then for schools, in this case, I was only interested in the number of fish that were in the school. Okay, so back to my original question. So how do seasonal and regional declines and marsh water level influence fish use of canals? So I had 2 models, a small fish and a large fish model, and a set of predictor variables. Season, which I had early dry, wet season, my 2 canals, and then marsh water depth, which I got from the data set. And then I used large fish density as a covariate in my small fish model. I used plot mix so I could apply a covariate structure to account for autocorrelation across sampling periods. Before we get to those results, this is just a hydrograph of the water level in the adjacent marsh to my canal. So in the L31W, water levels were already quite low when I started sampling. So this dark gray starts at 5 centimeters, and that's the depth at which fish are unable to access the marsh. So if you see dark shady, and that means small fish weren't able to leave the canal, and this kind of lighter color is the depth at which larger fish were unable to leave the canal. So I had it cut off 15 centimeters. So what you'll see here, the take-home message is in the L31W, water levels were already well below that threshold, and did start to rise slightly quicker than in the L7C. Okay, looking at the result for first the small fish model. I found a significant effect of season and canal. And when we look at this graphically, y-axis again is small fish density. My scale looks wonky because I not transformed the data just for use of, for looking at it here. defined as log units. And letters on top of the columns, if they're similar or if they're the same, means they're not significantly different from each other. So really the only significant differences we see are across canal. So higher densities of smaller fish in the L57C versus the L31W, but we don't see any differences within canal. There was some evidence that there was an effect of large fish density on small fish density. So here's a partial regression plot, and what this plot allows us to look at is just the effect of large fish density. So it parcels out the effect of water level. So what we see is that an increase in large fish density led to an increase in small fish density, at least in the L67C. This relationship does not really hold in the L31W, and that's kind of an ongoing trend in my data set, and that a lot of the patterns do not hold in the L31W. Looking at now my large fish model, again we see a season and canal interaction effect, as well as an effect of water level, which we didn't see in the small fish model. So first, I'm going to show you marsh water depth. So an increase in the adjacent, an increase in water level on the adjacent marsh led to a significant decrease of large fish in the L57C. Right, so as water levels rise in the adjacent marsh, larger fish are leaving the canal to move out. Again, we don't see this in the L31W. You'll notice that there's quite a few zeros water depth. And that's because the L31W is adjacent to a short hydrotreated wetland. I did not flood as frequently as the marshes adjacent to the L57C. So there's very few instances where large fish could actually leave, which could be why we didn't see this trend. And then looking at the season canal interaction, a little bit weird here in that we see an increase in large fish density from the early dry to dry. If water levels were already low, where are these fish coming from? Well, one thought I had was that as water levels in the canal itself start to drop, the fish may be clustering together towards the surface where there's better water quality conditions, or just that the canal itself is becoming smaller in size, that you're going to detect more individuals. And then as we would expect, a decrease in large fish density from the dry to wet season because they're leaving the canal and moving out to the adjacent marsh. Okay, moving on to my second question. So how do changes in hydrology affect the behavior of small fish and large fish? So in this case, I had three models, the probability of detecting a school, and then the schooling metric, so the nearest neighbor distance and distance centroid. I had a whole suite of predictor variables, looking at canal. Basic connectivity is just a different way to look at marsh water level. I won't go into it because it turns out it wasn't important anyway. And then large and small fish density. Instead of using p-values to evaluate the model, I use IPC's information criterion, or AIC. And what this allows us to do is run several models for each of my response variables. So I ran a model with just canal, with just large fish, small fish, and then the combinations. So you end up with a whole suite of models. And then you rank them based on their AIC score. The smaller the score, the better the model, so to speak. You also use R-squared to evaluate how good the model fit is. And then something called an evidence ratio, which just provides evidence, obviously, as to how good your best model is relative to other models. Okay, so here I'm showing you the schooling frequency model, and I'm only showing the top 5 best performing models out of all the ones I ran. And so looking at the R-squared, they were all actually very good models. So, and even these delta AICs, these are relatively small. And the evidence ratio, the way to interpret this is that, so this value says our best model, which is our first model, is 2 times better than this model. Our best model is 1.8 times better than that model, and so on and so forth. So what this tells us is all these are actually really good models. So then how do you pick your best one? Well, I went in and went with the approach that the simplest model is the way to go, which in this case would be just looking at small fish density. So small fish density is a good predictor of schooling frequency. And looking at that relationship graphically, there is a point out here, that's why this extends out. What we see is an increase in small fish density increases the probability of detecting a school. And when we get above around 5 individuals, that probability is over 50%. Okay, going on to my next model, which is nearest neighbor distance. Again, just showing you the top 5. You see much more of range of evidence ratio, which provides before that this first model really is the best model, and still a relatively high R squared value. So I picked the first model as my best model, which includes canal and large and small fish density. So what we see, an increase in large fish density leads to a decrease in that nearest neighbor distance. So the fish within a school become closer together, a school with more contact as more large fish into the picture. At least in the L67C. This relationship doesn't hold up in the L71W. And the same relationship is seen with small fish density. As we increase small fish density, these fish become more contact within the school. And lastly, looking at the distance to centroid, none of these models had great R squared values, they're all low, so interpret cautiously. But if we go with the season of the best model, we see there's some evidence that a decrease in the distance to centroid occurs from the early dry to dry season. So that's either indicative of the fish are becoming closer to their center, they're becoming more compact in shape. All right, on to my last question, which is looking at the diel patterns and the risk of predation. And here I was predicting both small and large fish density and their swimming speeds. And I used time of day, which is just day versus night, my 3 canals and the 3 months that I sampled. And then I use these metrics to measure a counter rate. So a counter rate is a function of prey density and their swimming speed, as well as something called the detection distance, which is just the distance at which a predator can detect prey. And I use some published values for that. So under high light conditions or daylight, the distance was 200 centimeters, and under low light or night conditions, I used 50 centimeters. And then if we multiply that by predator density, we get this following counter rate, which is just the number of predators and prey becoming encountered with one another on a per hour basis. So first I'm going to show you the individual metrics, and then I'll show you the model results. So just a quick hydrograph of what the water level conditions were like. Take a message here that the second sampling period, this April point, water levels were lowest across all canals. Okay, so just to run through these kind of quickly, here we're looking at small fish density across my 3 canals. And what I'm focusing on is significant changes from day to night. The little star indicates that there was a significant change. These occurred in the L67C, so we see a drop in small fish density from day to night. So where are they going? I'll wait on that point. They're not disappearing, but I do believe that they're moving somewhere else in the canal from where I am sampling. Whereas in the C111, we actually see an increase. So where are these fish coming from? For large fish density, the only significant trend was my last sampling point in the L31W. The fish densities were very low, at least for large fish. So a decrease from 1 to 0.1 per meter squared. That's still a relatively small value. And looking at their swimming speeds, large fish on the left, small fish on the right, there was some evidence to suggest that there was a decline from day to night, at least in the C111. You can see that large fish swim faster than smaller fish, just by looking at the y-axis. So if we put all those values together in our encounter rate model, for our y-axis is just total encounter rate, which is the number of predators and prey per cubic meter per hour across my 3 canals. Notice the scale on the C111 is much smaller, so fewer encounters in the C111. It is a very large canal. It's 30 to 35 meters wide and probably 4 to 5 meters deep. So the probability that there are some encounter with one another, at least on the scale that I measured, was very small. And then probably the trend that jumps out the most is that much lower encounters at night. There's some overlap from day to night, but overall, fewer encounters at night than during the day, and then we see a bit of variation from month to month. So just to summarize, how do seasonal and regional declines in water levels influence fish use of canals? Well, we found the strongest relationships in the L67C, and that a decrease in water levels in adjacent marsh led to an increase in large fish use of canals, and an increase in large fish density corresponded with an increase in small fish density. Now, we didn't see these trends in the L31W. One thought, which I mentioned earlier, was that there wasn't a whole lot of occasions where fish could actually use the canal, given that it's adjacent to short 100-year wetlands. And we do have some guys in our lab tracking larger fish that are in the canal and seeing when and where they leave. And what they've found is there's quite a bit of individual variation in large fish in the canal and how far they go. So some stay in the canal all the time, others leave and go kilometers, others go and just come right back. So there is a bit of individual variation, and I think some additional work is needed to really predict when and why large fish choose to stay or go. And why we may not have seen even trends with the small fish density in the L31W is there is quite a bit of structure along the edge. There's a lot of cover and overhang at various spots. So microhabitat structure in the L31W could be more important than some of these larger scale drivers, which we don't really see in the L57C. It's pretty much marched all the way through. So how do changes in hydrology affect the behavior? Well, it seems like the change in hydrology affected density, and then the density has then affected their behavior. So an increase in small fish density led to an increase in the probability of detecting a school, and an increase in both small and large fish density led to more compact schools with individuals closer together. And there was some evidence to suggest that a change in season led to a bit smaller distance enjoyed. And finally, is there a diel pattern in the risk of predation? Well, one thing I forgot to mention is that we didn't observe any schools at night, which is actually a very common thing. So it's good that we didn't observe schools at night. One reason is that they don't have the visual cue to group themselves. But then it led us to believe, ask where are these fish going? We saw that significant decline in the L57C, and one hypothesis that I proposed is that they are moving into the adjacent marsh. Now, according to the Eden data set, water levels were below that threshold. However, that's a 400 meter by 400 meter grid. And there's still quite a bit of ponding that occurred right along the edge. So what I suspect is happening is that there was in fact access to the adjacent marsh. And so at night, the smaller fish may be moving into the vegetation, either because it's safer or for foraging opportunities. And we didn't see that in the C111, but what we did see is that increase in fish density. And that's because I don't believe there was access to the adjacent marsh. And so they're just congregating right along the edge, so which is where I was reporting. So I would see an increase of their use of the edge habitat because it's still a safer and more profitable area than, let's say, the center of the canal. And in our encounter rate model, I found lower encounter rates at night, which may suggest that predation risk is higher during the day. But access to vegetation can certainly reduce the capture efficiency of predators. So I don't want to say that risk is high during the day because there's other factors that come into play. So just to offer a few conclusions, incorporating the characteristics of the landscape, in this case, the hydro period of the adjacent wetland, any sort of environmental gradient, change in hydrology that we see on a seasonal basis here, and then the temporal variation, which is the diel component of the study. All of this can influence predator-prey interaction. And using a field-based approach like I did helps you kind of capture all of these drivers. And then incorporating the knowledge of the behavior of the predator and prey, such as just swimming speeds or any sort of schooling behavior, can certainly provide better estimates of the encounter rate. So with that, I'd like to thank my WISE committee for guiding me along the way, as well as the funding sources from the USGS and Everglades National Park, and all those that have helped me out in the field. Going out in the Everglades, it was cool the first time. After about the 10th time, staying up till 2 in the morning, it gets old and people start getting crazy and really creepy. My bush was just right here. These guys were troopers, and I couldn't have done it without them, as well as the vast amounts of knowledge that I got from J. Matt and Joe, who could not be here today, our amazing former lab manager, Aaron Parker, who was strangling me a photo, and then our new, equally amazing lab manager, Allison, who keeps us all staying in the lab and make sure we all get out in the field when we're supposed to be. And with that, I will take any questions.
I thought I had mentioned that one of the things that's great for Anne is that she has a job. And so she's leaving at the end of this month and going to start a new job for a consulting firm in Baton Rouge. So, questions. What we usually do is we wait. The committee doesn't ask the questions until later. You guys have at it.
So I would struggle when we do visual surveys that we're double counting fish. So you're doing it per 5 minutes a video? How did you do with that?
So there is a chance that I was counting the same fish twice. However, one thing I noticed in my videos is that all fish they're all moving kind of the same direction. They're with the flow and parallel to the shore. I didn't see a whole lot of this going in and out of the edge. I mean, on occasion, and I would track the fish as best as I could. So there certainly is a chance that I'm counting at least in those 5-minute videos the same fish twice. I think the general trends that I see across seasons, it matches what we would have expected to see. So I feel pretty confident in those values. In order to reduce that, you'll notice, so for the 15-minute videos, I put them in the 30-second clip to really reduce that. So I mean, if I count all of 15 minutes, I'd be elevating that value quite a bit. So I try to reduce that by looking at the 30-second clip.
But you still just count every time you saw a fish, or if you saw one come in and get back? And
if I knew it was the same, I mean, if he left the frame and immediately came right back in the exact same spot, I assumed that was the same fish. If there was any sort of time that had passed, then that was counted as a new fish.
Sort of reason for the canal that you did?
There was already some data being collected in canals in our lab, so we had an idea of what species were there. And then I like the contrast between the L57C and the L41W because they're adjacent to different types of wetlands, right? The short hydrospheric versus the long. And then I added the C111 because I found it's kind of like an in-between of the L41W and the L57. So yes, there was some reasoning behind this canal.
No more questions, really? All right, well, let's thank you, Ann.